Okay, so for FRQ number 5, we have a pulley system with three masses, M1, M2, and M3. M2 and M3 have a mass of 5 kilograms, and M1 has a mass of 8 kilograms. There's two pulleys. So there's one pulley right here and another pulley right here. And M1 is hanging right here and attached to a string, which is connected to M2, which is on the incline. And M2 is then connected to M3 by a string over this pulley right here. All right. When the system is released, it's gonna accelerate either this direction or this direction, and that's what we're trying to find out in part A. Part A wants us to determine which way the system will move and justify clearly. So, and let's also note there is no friction on the inclined surface right here. All right. So to determine which way the system is going to move, I'm going to use Newton's. Total force of the system is equal to the total mass of the system times the acceleration of the system. All right. So, all right. Back to the diagram. So I have a force of Fg right here. I have a component of Fg right here, Fgx, and I have a Fg right here for M3. I know that these two are pointing in the same direction because this is going down to this way and this is going down this way, and this is opposing those two. Now I don't know which combination will be heavier, but by the looks of it, 5 and 5 makes 10 kilograms. So I'm just gonna make these positive and make this one negative and see where it goes. So the total force of the system is negative Fg1 plus Fg2x, the component of Fg2 in the x direction, or parallel to the surface, plus Fg3. And that's going to equal to M total times acceleration of the system. All right. Fg1 is M1 times G. Fg2x is equal to M2 times G times for every incline is a sine of theta, and the theta is the angle of the incline, which is 45. So 45 sine 45, and Fg3 is M3 times G. M total is the sum of all these masses, so M1 plus M2 plus M3 is times A system. I have all these numbers. I'm going to plug them in. So negative 8. So 8 kilograms is my M1 times 9.8 meters per second square. My M2 is 5 kilograms. G, once again, is 9.8 meters per second square. And times sine of 45 degrees. My M3 is also 5 kilograms. And G is 9.8 meters per second squared. That's going to equal to 8 kilograms plus 5 kilograms plus 5 kilograms. So that's the total mass. And times A system. Alright. So this whole term over here reduces down to, or this whole side reduces down to 5.248. The total mass of the system is 18, and then times acceleration of the system. Dividing 18 to this side, I get A system is equal to 0.292 meters per second squared. Now, since I got a positive acceleration by making Fg2 and and basically the forces of M2 and M3 positive. That means my acceleration is in the same direction as the forces of M2 and M3. So looking at the diagram, M2 and M3 forces are pointing this way. So that means the system will accelerate to the right. So the system will move right because A is going in the same direction as the forces acting on M2 and M3, which is right. Okay, so yeah. Now part B, we are asked to find the speed of M3 after it has traveled a total distance of 0.5 meters. Okay, so to do that, I'm going to use a kinematic equation. It is this: Vf squared minus Vi squared is equal to 2 times the acceleration times the distance traveled. All right. So for this problem, our Vf is the velocity at 0.5 meters, and square that. My Vi, initially the system wasn't moving, so this is 0. This is going to be equal to 2 times the acceleration times the distance traveled. All right. So isolating for the velocity, what I'm trying to find, I get V at D is equal to 0.5 is equal to square root of 2AD, plugging in my numbers for this side. My acceleration is found up here is 0.292 meters per second squared, and my distance traveled is 0.5 meters. And so plugging this into the calculator, I get 0.54 meters per second. Now it asks for speed, and since this is already positive, this is my speed, even though I saw for velocity. Alright, part C wants me to calculate the time it takes for M3 to cover the first 0.5 in part B. Alright, so for part C, I'm going to use a different kinematic equation. And it is this: D is equal to Vi times T plus 1/2 times A times T squared. Okay, so my distance traveled is 0.5 meters. My Vi is 0, so this whole term cancels out. My acceleration I found up here is 0.292 meters per second squared, and my T is what I'm trying to find, so T squared. Alright, so if I isolate for T, I'm going to multiply 2, divide by 0.292, and square root everything. So T is going to equal to 0.5 times 2 first, then divide by 0.292, and then square root everything. Alright, plugging this in the calculator, I get 1.852 seconds as my time. Alright, now part D wants us to use ratios to find the time it takes for M3 to travel an additional 0.5 meters. So basically the time it takes to travel the second 0.5 from 0.5 to 1 meter. Alright, so first of all, the first 0.5 meters, I'm going to define the time for it first. For the first 0.5 meters, I'm going to use this Kinect equation. It's called D1 is equal to VI T plus 1/2 A T squared. And so, first of all, this term cancels out. And if I isolate for T, let's call it T1 because this is gonna be a different time. T1, my T1 is gonna be equal to, so D1 times 2, so 2D1, then divide by A, and then square root everything. So that is my T1. Now I'm going to define the time it takes for the object for M3 to travel a full meter, so 1 meter. So this time the distance is twice of the initial, so 2D1 is equal to VIT plus 1/2 A times T, let's call this T total square. All right, so isolating for T total, wait, this term cancels out first. Isolate for T total, I'm going to multiply 2 over, so T total is going to be equal to 4D1, then I divide by A, and then I square root everything. So that is my T total. Now, relative to my T1, T total, or these two have a common term that I can put, basically I can plug this into this equation. So if I plug this in for this one, or if I sub in T1 for a partial of this term, I'm going to get square root of 2 T1, because square root of 2, basically this is equal to 2 times the square root of 2D1 over A. So basically what I did was I subbed in T1 for here, and I left the square root of 2 alone. So this is what I get. This is the ratio, a ratio that I got. This is relative to T total, not the second 0.5. Now I'm going to deal with the second 0.5 meters. So second 0.5 meters, I'm going to call this T2, and T2 is equal to T total minus T1. And so T total is square root of T1. T1 is T1. So T2 is going to be equal to, so square root of 2 minus 1 is 0.414, and then I have T1 as my coefficient. So this is essentially the ratio I'm looking for right here. T2 is equal to 0.414 of T1. So now that I have this ratio, I'm going to plug in T1 to help me find T2. T1 I've already found up here to be 1.852 seconds. So T2 is going to be equal to 0.414 of T1, so 1.852 seconds. And then plugging this in the calculator, I'm going to get 0.767 seconds. All right. Part E, we want you asked us to use ratio to find the speed of M3 after it has traveled at this total distance of 1 meter. All right. So I'm gonna do a similar thing. So first I'm going to define the velocity at d equals 0.5 first, and then I'm going to define the velocity at d equals 1 meter, and then I'm going to set up a ratio and then use that to help me find the velocity at d equals 1 meter. All right, so velocity at d equals 0.5 meter. So v at d equals 0.5 meter. I've already defined it up here. It is equal to square root of 2AD. 2AD. I'm going to call this D1 because there's going to be a different D, which is 1 meter. So let's call this D1. All right. Now for velocity at d equals 1 meter. I'm going to start from the beginning. So using this kinematic equation, vf squared minus vi squared is equal to 2 times a times, now since the distance is 1 meter, this is twice of the initial distance right here. So this is d1 and this. And so this means that this d is going to be 2d1. Yeah. All right. So vi is 0. And then if I want to solve for vf is essentially what I'm looking for. Vf in this case is v at d equals 1 meter. And if I want to solve for it, I'm going to have to square root this side over here. So it's going to be a square root of 4AD1. All right. So similar thing to the other part, square root of 4AD1 is equal to square root of 2 times square root of 2AD1. And it looks similar to this one right here, right? So I can sub this in for this one. So sub in v at d equals 0.5 for this term. So the ratio is v at d equals 1 meter is going to be equal to square root of 2 times v at d equals 0.5 meter. So that's my ratio. All right. This is the ratio right here. Now that I have that, I'm going to plug in my what I have to find v at d equals 1 meter. All right. So v at d equals 1 meter is going to be equal to square root of 2 times v at d equals 0.5 meter, which I found up here to be 0.540 meters per second. So 0.540 meters per second. And plugging this in the calculator, my answer is 0.764 meters per second for v at d equals 1 meter. Don't ever make us do this v over d. Come on, man. Okay. Part F. Now we are asked to find the acceleration of m2. Oops. Well, the acceleration is the same throughout the system, and I've already found it up here. So I guess that's the answer. Acceleration is same throughout whole system. So a acceleration of m2 is equal to the acceleration of the system, which is 0.292 meters per second square. All right. Now part G wants us to calculate the tension of in the string connecting M1 and M2. So basically this thing right here. All right. So to do that, I'm going to focus on the forces acting on M1 and use Newton's second law to help me find the tension. All right. So as I said, I'm going to focus on M1. So the total force on M1 is equal to M1 times A. Now, I know that the system is going to move this side, so T1 must be bigger than Fg. So I'm going to put that as positive first. I'm going to call it tension T1 and minus Fg of Fg1. And that's going to be equal to M1 times A. So isolating for T1, I'm going to add this over, or add Fg1 over. So T1 is equal to Fg1 plus M1A. Fg1 is M1 times G, so I'm going to sub that in right now. T1 is equal to M1G plus M1A. All right, so now that I have the equation, I'm just going to plug in my numbers. So T1 is equal to M1 is 8 kilograms. G is 9.8 meters per second square. Plus M1, once again, is 8 kilograms. And the acceleration we found up here is 0.292 meters per second square. Plug this whole thing in the calculator, we get 80.733, and the unit is newtons. So there's a tension of the string connecting M1 and M2. Part G asks us to find the coefficient of friction along the surface of the incline in order to keep the system stationary. All right. So I'm going to use Newton's second law to do this once again. So total force on a system is equal to M total in the system plus times A, the acceleration of the system. Now, since we want to keep this system stationary, the acceleration of the system is going to be equal to 0 meters per second square. All right, so once again, I'm going to set up or plug in all my forces, which I know to be similar to up here. So I got Fg3 plus Fg2x minus Fg1, and now I have I have friction, so I also have a Fs. And then since my acceleration is 0, this whole side is going to be 0, so all of this is going to be equal to 0. All right, so first of all, I'm going to define my force of friction. Fs is equal to mu s times m2 times g times cosine of 45. So now I'm going to plug that into the equation. So Fg3 is m3 times g. Fg2 is m2 times g sine of 45. Fg1 is m1g and Fs is all of this minus mu us m2g cosine of 45. Oh, by the way, since if it's not clear, this is basically the normal force right here. Friction is mu times Fn, and Fn is equal to this whole thing right here. There. And the reason it's M2 is because M2 is the one causing Fn. Alright. So we wanna solve for mu the coefficient. So I'm gonna add this to this. Wait, hold on. I'm going to add this to this side. So m3g plus m2g sine of 45 degrees minus m1g is equal to mu s m2g cosine of 45 degrees. All right, we want to solve for mu s, so we're gonna divide everything in parentheses to the side. So mu s is going to be equal to all of this, so m3g plus m2g sine of 45 minus m1g, and divide by what we divide here, so m2 g and cosine of 45. Alright, now I'm going to plug in this whole mess, plug in all the numbers for the variables. M3 is 5 kilograms, G is 9.8 meters per second squared. M2 is 5 kilograms as well, G is 9.8 meters per second squared. Sine of 45 minus M1 is 8 kilograms and G is 9.8 meters per second squared. Sorry. And M2 is 5 kilograms, G is 9.8 meters per second squared, and cosine of 45 degrees. Alright. Plugging this whole mess in the calculator, we get 0.151 as our coefficient of static friction.